Welcome to lecture number 40, subject Introduction to Mechanical Engineering, module 5. Myself, Dr. Sachindra Kumar Rao, Department of Mechanical Engineering, C.V. Raman Global University, Bhubaneswar. Today we will discuss Carnot Cycle. So it is an important cycle. So learning outcomes. Today we will discuss reversible and irreversible processes. Then we will elaborately discuss about the Carnot cycle. So what is reversible and irreversible process? It is very important before understanding Carnot cycle because it will play a vital role to understand a Carnot cycle. So first of all, a reversible process is a process in which end of the process both the surrounding and the system come back to its original position, or we can say a reversible process is defined as a process that can be reversed without leaving any trace to the both surrounding and system. So in the end of this process, you will find system and surrounding, they are returned back to their original position or initial state after completion of the process. So the process is possible only if the net heat and net work exchange between the system and the surrounding is zero. For the combined process that are not reversible process is known as irreversible process. So there are factors which are responsible for irreversibilities are frictions, unrestrained expansion, mixing of two fluids, heat transfer across finite temperature differences, electrical resistance, chemical reactions. So these are the factors which causes a reversible process to irreversible process. So again, these reversible and reversible processes are divided category into three types. One is internally reversible. If there are no internally irreversibilities, or within the boundaries there is no irreversibilities, then we can say that it is internally reversible. If there are irreversibility or no irreversibility outside the boundary, that means in the surrounding, then we call that it is externally reversible. If a system having internally reversible and externally reversible, we call it totally reversible or simply reversible. So with this concept, we move to the Carnot cycle. This cycle is the reversible cycle which was proposed by Sadi Carnot in the year 1824. So it is considered as the fundamental cycle. We compare all the practical cycles with these cycles. So there are basically four processes, and the cycle and the engine which operate on this cycle is known as Carnot heat engine. And let's say one by one. Number one, the first process is reversible isothermal process. Let's understand this process. Here you can see there is a system piston and cylinder arrangement where the one end is attached to its source. It is having a temperature TH. So the first process is reversible isothermal expansion. That means there are two isothermal expansion, there are two isothermal process and two adiabatic processes. So let's start with the first process, a reversible isothermal process, in which the one end is connected to a source, a heat source, where heat is added to the system with a constant temperature. So as heat is added to the system, there is an increase in temperature, and infinitesimal small amount of heat increases, the piston starts moving, and as a result the heat required it will take from the heat source. So the process, the expansion process continues with a constant temperature. Now you can see one in a PV diagram, 1 to 2 there is a heat addition at a constant temperature process. Then the next process is reversible adiabatic expansions. So from 2 to 3, the process you can see here, now the end is insulated, so now the expansion process continues, so the temperature decreases from TS to TL. So the temperature decreases but the expansion process continues up to 0.3. So now the next process is reversible isothermal compression. Now we make it and attach to another another heat source or sink we call it, because we are rejecting heat to this medium. So the piston goes back or compress here, so that the position moves from 3 to 4, and there is a heat, whatever the heat is releasing or heat is generating due to the compression, that is rejecting to this medium, and there is a constant temperature maintained throughout the process. So it is a constant isothermal compression process 3 to 4, you can see in the PV diagram here, where heat is rejecting to the sink. Now 4 to 1, it is a reversible adiabatic compression. So you can see in the position, the end is the where the sink is attached, it was now insulated. The piston come back to its original position 1, where it is beginning of the process. Now the cycle continues. Here you can see 1 to 4, it is a reversible adiabatic compression. So now the total cycle, the cycle complete. It is started from 1 and come back to the original position 1. Now one cycle complete. Now we will see what is the amount of heat transfer or work transfer during the process, due to completing a cycle. Let's say under a PV diagram, the area under a curve will give you the work transfer. Now during expansion process from 1 to 3, it will give you the area under this curve will give you the work transfer during the expansion. Similarly 3, 4, 1, this process will give you the compression process, where the area will give you the work transfer during the compression process. Now the net summation means area under 1, 2, 3 and area under 1, 4, 3. If you subtract it, you will find the area 1, 2, 3, 4, 1. This is the area which will give you the net work interaction or transfer during the one cycle. So now this is the previous one was for a engine. Whenever we reverse the direction of heat flow, previously we have seen clockwise heat transfer, you have seen there is a clockwise heat transfer during a engine, but if we will just reverse the direction, we call it a reverse Carnot cycle. It is for a heat pump or refrigerator. Here you can see heat is added from the sink and heat is rejected to a source, and the directions are counterclockwise. It is a reverse Carnot cycle. There are two principles from this concept. Number one, the efficiency of an irreversible heat engine is always less than the efficiency of a reversible one operating between the same temperature range. That means any irreversible heat engine having a less efficiency than that of a reversible heat engine. It is one corollary, and second one is the efficiency of the all reversible heat engine operating between same two reservoir will have the same efficiency. That means one case it is saying irreversible heat engine performance is less than reversible heat engine, and another one is if there are more than one heat engine operating with two different operating temperature, then they are having a same performance. So we can prove it by if one statement is violating it, then definitely it will be violating our second law. So by this method we will prove it. So to prove it, let's say assume there are two heat engines, one is reversible, another is irreversible. So you can see in irreversible heat engine there is a amount of heat it is taking QS, and the work producing W irreversibility, this is the work producing, and the QL is the amount of heat is rejecting to the low temperature reservoir or to the sink. Now the same concept also for this heat engine, and but it is a reversible one. Now to proving it, let's say assume the work produced during irreversible heat engine having greater than reversible engine, because we are violating the point 1. So in this case what we will do, we can write down W irreversible is greater than W reversible. Okay. Now let's convert this heat engine to a heat pump, so that the same amount of heat it will taking same amount of work it is taking, and it is transferring the amount of QL from this sink to the heat to the source is QS, so that as a net effect it is transferring QH to this heat engine, irreversible heat engine, and it is transferring it is taking rejecting heat QH to the source, and the net effect will be 0. Here adding, here adding QH, here subtracting QH, so now the net effect is 0. As a result, we will get this type of machines after combining the irreversible heat engine and the reversible heat engine refrigerator. So we will find out this concept. So here we will find out there is no effect because QS it is taking and QH is rejecting, so that there will be no heat is from the sink from the source. So now the machine operating like this, the net effect, that means W irreversibility, amount of work transfer due to irreversibility W irreversible, and the work taking due to the refrigerator W are reversible, because it is greater than W reversible. So we will get the net effect W irreversible minus W reversible. This is the net effect. Similar manner, it is QL reversible minus QL irreversible, and there is no heat transferring or rejecting to the surrounding. That means it is violating the second law of thermodynamics. Clausius statement it is violating. So it is taking a low temperature. It is the Kelvin Planck statement. That means it is operating at a single reservoir. So we proved that once we violating one statement, it definitely violates the second law of thermodynamics. So that in this manner we can also prove the second statement. So this is these are the two corollary of the or two principle of the Carnot cycle. And we have seen already Carnot heat engine, where it is taking a heat from a source and rejecting some amount of heat to a low temperature zone, that means sink, and some amount of work is producing. So it says that the performance can be measured in terms of efficiency, thermal efficiency is equal to 1 minus QL by QH. From the Carnot cycle, from temperature scale, we have seen that QH by QL is equal to TS by TL, or this performance, the thermal efficiency, or you can say Carnot efficiency, can be written like this. Carnot efficiency or thermal efficiency for a reversible cycle is equal to 1 minus TL by TH. So this term for the heat engine, and this is for the Carnot efficiency or thermal efficiency for a reversible cycle. Similar manner, you can go for a refrigerator or heat pump. Already we have discussed about this refrigerator and heat pump, the difference between these two machines, but the operating principle is same, where it is taking some amount of heat from a cold body and rejecting heat to a hot body by taking some amount of external work. So the performance can be measured in terms of COP, coefficient of performance. It is equal to 1 by QS by QL per QC, or we can say from low temperature it is taking minus 1, or COP of a refrigerator is equal to 1 by TH minus TL minus 1. Similar manner for heat pump, COP of heat pump is equal to 1 by 1 minus QL or QC by QS is equal to COP of heat pump of refrigerator is equal to 1 by 1 minus TL by TH. And already we have proved COP of heat pump is equal to 1 plus COP of refrigerator. So these are the concepts which we have discussed in this class, and in the next class we will discuss about the working principle of a steam power plant, the concept, the theory behind a steam power plant in the next class. And these are the references we have followed to prepare this lecture. And if you have any questions, you can write to me with this email ID. Thank you.